Hello everyone. Yeah, this is Dr. Nung Yi. So I'm teaching the ceramic part for MS 3011. Okay, so the textbook should be the same as Prof. Raju's one. So it's it's different one. It's a fundamental ceramics. So I get most of the contents from this book, Fundamentals of Ceramics. And this is a timetable. So this is the first week, introduction of ceramics. Then week 8 and week 9 is going to talk about this processing of ceramics. Okay, so next week there will be no tutorials because the tutorial is before the class, right? So our first tutorial start in week 9, so which is after the processing of ceramic 1. Okay, so the tutorial 1 start in week 9. Then the quiz, please mark your calendar. So calendar which is week 10. Week 10. Okay, so this one will be 33 points, 33%, which means 33 points here. Okay, so it's only my part. So basically week 7 to week 9 contents. Okay, so these 3 weeks will be the quiz 2. Then follow the quiz week will be week 11. So will be properties of ceramics. So in this one, I'm going to give you lamps. So this lamps you have to go through by yourself. There's a lot of interactive questions. Please try your best to answer it. Okay, and because there's quite a lot of math manipulation there, so I think it's better I put a lamp sequence. So the week 12, property of ceramic 2. Okay, the tutorial will be in the week 12. Okay, so the quiz will be the last week. Last week of quiz 13, week 13 will be the last quiz. So please bear in mind, quiz 3 will also cover half of the quiz 3 is covered from Prof. Raju's part. So please remember to review his part. Okay, so I have to emphasize here because every year we're going to have students have MC'd their CAs. So there always be makeup. So there's no way to run out from any CA. Okay, so you must have marks for CA. Okay, so we have 3 CA here, quiz 1, quiz 2, quiz 3. So no matter what, we'll always give you a makeup. Okay, even you have a MC for makeup, we still give you another makeup until you have a marks for this one. Okay, so please bear this in mind. This is a new rule. This is a new rule in school from this semester. So since because the percentage is very high for CE and there's no final, especially for my course, there's no final. So we have to make sure everyone have to go through all the quizzes. It's not like the previous years, you can use MC to MC a few. Okay, so just please bear in mind, no matter what, try your best. Definitely you have to take all these CAs. Okay, quiz 2 or quiz 3. Okay, is that clear? Yeah, okay, this is super important. I think it's from this semester, school emphasize this one. So nobody can use MC to escape any of the quiz. Okay, thanks. Okay, so the whole general object of this subject is you can learn some general knowledge on ceramic materials and also understand the concept of process, structure, and the property. Okay, as a material scientist, I always said these are the 3 important things. Process, how can we make certain materials? What is the structure of the materials? What is the property of the materials? Okay, so you can see this course, right? We also arranged in this way. If you see the one, you can see the process, the properties. Okay, and this week we'll talk about the microstructures. Okay, so it's always arranged in this way. So you should know the process, structure, and the properties. Okay, and get specific knowledge on processing of ceramics. So in this part, I will spend a lot of time explaining sintering from very fundamentals. All these fundamental equations of mass manipulations I'm going to cover, and then we can derive the equations and use equations. We can get some general understandings how a ceramic is processed. How can we control the microstructures? Understand and be familiar with the property enhancement of ceramics. Okay, so since we know the process and structure and property are closely linked with each other, these 3 things are closely linked with each other. So let me try to write something here. Okay. Super super important. The three things are very, very important. Okay, so you have to know the interrelationship between three of them. Okay, so this week, normally the first week is always a happy week, right? So it's just some random and general things. So it will be very easier for you. So let's just go through very leisurely, basically. Okay, so in this week, we're going to have three parts: the introduction and the crystal structure of ceramics, and the characteristics of ceramics and applications. Okay, so let's move to the first one, the introductions. So what are the ceramics? Okay, so you're also, this is objective. So understand the bond, the chemical bond, understand the concept of crystal structures, and also you have to know how to calculate the minimal cation to ion radius ratio for coordination number. So can you please mark this one as a VIP part? Yeah, this portion are very, very important. Okay, so it's one of the key components in this week. Okay, calculate the minimal tight ion to ion radius ratio for coordination number. Okay, and understand the crystal structures for some typical ceramics. Okay, understand the characteristic and applications of ceramics. Okay, so these are the objectives. So let's move to the first week. Okay, our first part, the definition of ceramics. Okay, so we can read through. The ceramic can be defined as solid compound. Okay, so you can see the process. Most of the process you have to apply heat. Okay, so which means you have to heat up. Okay, or sometimes even give you pressure, heat and pressure together. Okay, and also all ceramics comprise at least two elements. Okay, so provided one of them is non-metal. So the other one may be metal or non-metal. So for example, you have A and B. So you compound them. So the B, so you must have one. Okay, the B must be a non-metal. That must be a non-metal. Okay, just like this one, magnesium oxide and silica carbide. So oxygen is a non-metal, right? Actually, carbon is also non-metal, and also the other one. So we can see the other one may be metal or non-metal. So which means your A can be metal. Sorry, the one is not easy to write. So like magnesium is a metal or a non-metal, like silicon is a non-metal. Okay, so actually it's very easy to remember this one, right? No matter what, you must have something which is non-metal. Once you have a non-metal, so it's going to be a ceramic. Okay. So let's continue. You can see, so these are the ones used in the, like people make the rice bowl, the porcelains, and what's inside, heat up very high temperatures. And in modern days, like what you are going to see in heat treatment lab in B2, in MSE, so you will see a lot of this type of furnace. So they use this electricity to heat up. We call it electric furnace. Okay. So these are the metals. Metals are the light blue one, and the green one is metanoid, and this color, which is non-metal. Okay, so no matter what, you have to have non-metal. Okay, so these are some of the very typical ceramics like oxide, magnesium, aluminum, iron oxide. All these are very famous one. And the carbide, silicon carbide, boron carbide, and the titanium carbide, and nitride, boron nitride, boride, titanium boride, like a silicide, iron silicide, titanium silicide. Okay, so just some general information is like my handphone, Okay, the handphone, most of the handphone, 90% of the materials used in handphone is ceramics. So you can imagine how important ceramic is in the modern technology. Okay, so it is very widely used as one of the materials compared with metal and polymers. Okay, so the forms of ceramics, so mostly like people say, hey, this is bark, which means it's a big one. So the bark one. So some are fibers. You can see the fibers diameter here is only about 10 micron. 10 micron. It's roughly same as your hair. Roughly the microns. Okay, and also thin films. In this case, right, you can see this is substrate. Okay, so on top you have an interface between the substrate. It is interface, and then this is interface. Okay, then this is thickness of film. So you can see the signature form. Okay, so same form. Okay, so you just deposit on top of something. Okay, so these are some forms of ceramics. Okay, so now move to a very important part, since we just said 3 big things of any materials, right? Structures. So structures have different levels. Okay, structures have different levels. So when you do your FYP, so you have to let people know what is the structure level you're talking about. It is a subatomic, it is atomic, or it is nano, or it is micron, or it is macro. Okay, so you can see this is increasingly become bigger and bigger and bigger, right? Okay, let's start from the smallest level. The smallest level is subatomic structures, such as what are the bondings, is ionic bonding or metallic bonding, blah, blah, blah. You can talk about valence, the Bohr atomic model. Okay, so these are the very subatomic structures. Okay, then we come to the atomic level. Atomic level, then you're going to say how your atom is going to be arranged. Okay, so if let's say if you do your FYP, so your supervisor say, hey, can you tell me what is the atomic level of these materials? So basically what they're asking you is about how this crystal is arranged. For example, you have crystalline, you have amorphous, right? And crystalline, so what is the structure there? Okay. So in your FYP, but most of FYP students cannot use the machine, they call the TEM. Okay, TEM. I think in year 4, you're going to learn all these skills. Okay, and also use XRD, X-ray diffraction pattern. These machines can help you to say what is the atomic level of your materials. Okay, so you're going to learn all these tools in your year 4. Okay, because you're year 3 already, right? I think most of you, only a few maybe from year 2, but most of you are year 3. So next semester, you're going to do your FYP. So I'm just giving you some big things here. So in that, so first, most of you is going to fabricate something. You come out and make something, then you need to use different machines to say it's to request characterization, which means we need to understand the microstructures of the materials. For example, you can use XRD and TEM to say the atomic level, how the atom is arranged. Okay, so this is atomic level. So structure compose of the organization of how the atoms and molecules relative to each other. Okay, so this is atomic level. Then you can move to the nano level. Okay, so how the arranged of a small structures in nano orders, like this one is a very typical request, a CNT, carbon nano tube. CNT. Okay, carbon nanotube. Okay, so you can see most of the nanocarbon tube. So the diameter, is like 10 nanometers or like 20 nanometers. Okay, so a range of small structures in the nano range. Okay, and also then microstructures. So this is a level most of you is going to face in your FYP. Okay, like a range of small structure can be identified by the microscope. So in this level, people can use like SEM or even like optical microscope to say, so how the grains arrange with each other. So what is the grain boundaries, okay, what's the porosities? So this is the even bigger level. Like in this region is like a micron already, okay? And the last one is macro, is what you can see already, okay? Okay, so remember this one. So this is a very, very fundamental. So once you have this 9, okay, every time you do a project, you have to have a big picture first. Okay, the big picture. So what are the supervisor, what the requirement from the supervisor? So the supervisor may want to know the subatomic. Most of the time, we want to ask about this one. Okay, most of us will ask you what is the atomic arrangement of your materials, what is the nanostructures of the materials, what is the microscopic structures of materials. So you have to use different machines to understand its structures in different ways. Okay. So let me continue. Okay, so now we move to the first level. So first level is what? The first level is subatomic. Okay, actually in this case, it is pretty straightforward. So we need to understand material is ionic bonding or covalent bonding. So in order to, I think you learned this before, but let's just quick review what you learned in your year 1 course. Okay, so how can we determine it's ionic or covalent? Okay, it's pretty straightforward. So we can use this this table. So you can see all these figures here. these figures here. So these figures we call the electron activity. So what is activity? So it is actually defined as a relative tendency of atoms to accept an electrons become an ions. So obviously, so this one is the highest one. I can say 4, 3, 2.8. Okay, it's very high. But for this column, it is very low. Okay, so obviously, so if you move from this way, so the electrical activity is higher and higher and higher. Okay, so you can see, so if you're increasing on the right hand side, so it become readily accept electrons. So left hand side is give up the valence electrons. Okay, so this people just trying to quantify. Okay, so strong electronegative atoms is ready to accept electrons, as we said, become ions. Okay, so it is so how can we determine it is an ionic bond or covalent bond? Okay, so I think we are very comfortable with this already. So there's two types of chemical bond in ceramics. So in ceramics, there are mainly two bonds, the covalent and the ionic. Okay, so it can be mixture. Okay, mixture, mix of ionic and mix of covalent. Okay, so ionic is a character involving transfer of bonding from cation ion to ions. Okay, and covalent is very simple. CO means they have to share. Okay, share involving the orbital sharing of electrons. Okay, so this is the most simple one. Like sodium chloride. You know, sodium is here, right? Sodium is here. Chloride is here. Okay, so very, very far away, right? So if on the periodic table, if they're very distant, very far away, okay? So they are occurs between the positive and negative ions. So in this case, your transfer, give it to you, okay? So we know that there's a large difference in the electroactivity. So for example, we said there's a sodium chloride. This is our most typical examples. So actually, so let's continue. Okay. So covalent is always sharing, so requires shared electrons like a carbon. Okay, so carbon and hydrogen in this case, so share them. Okay, share electrons from hydrogen and share electrons from carbon in this case, and because carbon and hydrogen they have very close electron activity. Okay, so the thing is, so why we still repeat what we learned before? Because there's a very important concept. Okay, please write down. In ceramic, so there's a mixture of covalent and ionic. Some students ask. Yes. Yeah, Hong you asked the correct question. Okay, that's I stop here to let you know. Okay, so okay, this is a very good question. So why we still review this is because ceramic is going to have a mixture of ionic and covalent. So how can we determine it is more ionic or it is more covalent? So roughly, what is the percentage? Actually, there's an equation. Okay, so in ceramic compound, can you write down? In ceramic compound, AB, most are partially ionic and covalent. This is very important. Normally more ionic. Okay, so it's partially, half, not half, partially, ionic and covalent. Okay, so also even equation, but it doesn't matter. Okay, so anyway, if you can write down, so ionic character percentage. So what's the percentage of ionic? So actually it's 1 minus exponential minus 0.25 x A. So what is this x? X is just electronegativity, as what I have already said in the in this, right, all these numbers. Okay, so electronegativity. Actually, the principle is also very straightforward, right? So you can see if x minus b is bigger, so this percentage of ionic character is bigger or lower. Can you write in the chat box? If x and b, the difference is bigger, so the ionic character, the percentage is higher or lower. So this one is bigger, right? So then because you have a minus here, so it will be lower. Then you have another minus here, so we're going to higher again. Okay? Okay, so which means x XA and XB is bigger, so which means your ionic character will be bigger. Okay, so it's a common sense, right? As we already know. So in the periodic table, if you're further away, okay, so which means you're most likely is going to share or become an ionic bond. Okay, but if you come closer, you are more stable. Okay, so we'll be more covalent. Okay, so this is just a very rough guide of how can you determine something is more ionic or more covalent. We never use it. Okay, I just let you roughly know there's such things here. Okay. So let me quickly go forward. Okay, so now so far we have finished what? We've finished the subatomic, right? Subatomic, the essence of subatomic is ceramic is a mixture of the covalent and ionic. Okay, this is very important. Very important. So let's continue. Okay, so now we move to the next level. So next level, what we call is atomic level. Atomic level is how the atom is arranged. So you also know this, right? The crystalline, most like metal, most ceramics and some polymers are crystalline. Of course, in ceramics, please just the glass. The glass is a very amorphous material. Okay, so glass is amorphous materials. Okay, so amorphous means which means your atom is not arranged in an ordered way. It's a very complex structures. So most of the amorphous they are processed under very rapid cooling. Okay, which means you cool very fast. Okay, so this is atomic level. So in atomic level, we know big thing is we have a crystalline and amorphous. In crystalline, so now let's try to understand what's in crystalline. So in crystalline, you have 7 crystal systems and 14 crystal lattice. You also learned this before, right? The cubic, the tetragonal, the orthorhombic, the hexagonal, the monoclinic, the triclinic, and rhombohedral. Okay, so you learned this before. So in the cubic, we have a simple cubic, body-centered, FCC. Okay, so all this you learned before. I just summarized everything in the same slides. Okay, for you to clarify. Okay, so when you do any materials research, right? So you have to know what the level you're talking about. Is it subatomic or it is atomic? So if it's atomic, then first of all, you have to know it is a crystalline or it is amorphous. If it's a crystalline, so then you have to know it is a simple cubic or if it's a body-centered tetragonal or it's a hexagonal. Okay, so you have to be very clear your mind here. Okay, don't get confused yourself. Okay, so these are the atomic level. So then this unit cell, which is the smallest region of space, we repeat it to describe the 3D pattern of the atoms of a crystal. Okay, so move to the third level. The third level is nanostructured materials. Nanostructured materials. How can we define something as nanomaterials? You know, so a lot of professors in NTU, MSc is doing like nanomaterials, including myself. Okay, myself is very much this one. Okay, so if you're interested to talk about your FYP, also if you're interested in SimFarm, you can talk to me. Okay, so SimFarm, I'm a SimFarm person. Okay, so anyway, so the nanostructure means what? Means at least one dimension falls into nano range, like nanoparticles. Particles of this range, it is everywhere. Everywhere is nanometer range, right? Nanometer range. Okay, so 1D. So 1D, which is nanorod, as we just said. Okay, so you can imagine this is just dot. This is just like a pencil. So this is just like a paper. This is 2D, 1D, and 0D. Okay, so in the 1D, so it's a nanorod or nanowire because the diameter, only the diameter, it is okay, where's my, okay. Only the diameter is in the nano range. So the length may not be, the length can even be like micron range. Okay, so for the 2D, so you have this thickness, or the film is in the nano range. The thickness is in nano range. Okay, so this one is we call it a SimFarm structures. Okay, so SimFarm is like paper. Okay, 1D is like pencil. So 0D is just dot. Okay. Then beside all this 0D, 1D, 2D, so we have special structures like micron, mass porous, cold shell, organic, hybrid, nanocomposite, and many, many more. So if any of the dimensions falls in the nano range, so we say it's a nanomaterials, nano structures. Okay, so this level is nano level. So now we move to something which is maybe more related with FYP. Okay, so this one now we call it microstructures. Microstructures, like you can see a lot of green boundaries, green boundaries, green boundaries. Okay, so in each grain you have different orientations of your atoms. So like in this case, the crystal orientation is this direction, right? Crystal orientation. But in this one, so change a little bit, so we change to this one. Okay, so you can see they have a different crystal orientation in different grains, and in between we have grain boundaries. Okay, so the question you're going to ask yourself when you do FYP, right? So if your supervisor asks you, hey, can you tell me the microstructure of your materials? So then you're going to use SEM, right? In this one, you use this machine, SEM. In the FACS lab, in the SEM, using SEM to say your samples. Okay, then what are you going to say? So all these things are the possible things you have to let your supervisor know. So what are the shapes? What are the size of your grain? What is the shape? How big is this grain? So what the shape is, a round shape or is some very odd shape, hexagonal shape or whatever shape? Okay, the shape and the size of grains are together. Where are the pores? Do you have any pores here? Do you have any pores here? Do you have any like pores even inside? Most likely will be at the grain boundaries. Okay, so where are the pores? Do you have any second phase? Any impurities? Where are the impurities? So you have inside A here, maybe in the grain boundary B. Okay, you have to let your supervisor know. Okay, and what the distributions? How this second phase distributed? How the porosity distributed? What are the percentage? So all these things. Why it is important? Because all these like a shape and size and porosities and second phase and the distributions, all these things determine the properties of your materials. Okay, so that's why it's so important. Okay, so please know this one because when you do FYP, because my previous experience is student set me to do SEM. I don't know what I'm going to exam. You might put under the microscope. I don't know what I'm looking at. Okay, so all this is what you're going to look at. Okay, what are they? Okay, trying to find out all these things. Okay, so this is a microstructure range. You can say this is almost the biggest one, biggest level already, because the next level is macro lines, what your eyes can see already. Okay, so this everything is still in a micron level. Okay. Okay, so so far we finished different levels of structures of ceramics. Okay, so let's move on. So some terms, since you're a material scientist, okay, so people will say all sorts of like terms, some names you may not know. Okay, so there are some categories when people talk about the traditional materials like traditional ceramics and advanced ceramics. What the difference? Okay, you can see the major difference is what? The traditional bulk ceramic, it is actually most of people talk about is microstructures or nanostructures. Okay, in the traditional ceramic, the structures is very coarse, it's non-uniform, and it is multi-phase, which means you have a lot of impurities. It's everywhere. It's difficult to control the uniformity, and it's very coarse. Okay, but advanced ceramic, which means at least an order of magnitude finer. So the grain become finer and it's much more uniform. Everywhere is the same, much less porosities. So actually in one word, so what is the advanced ceramics? It is much controlled. So your morphology, it is much more controlled, much finer, much homogeneous, much more uniform, and the porosity is much more controlled. Okay, so these are the advanced ceramics. Okay, so obviously it's more difficult. So if you work in industry, you know your job, you're an engineer, the job is to control. You have to control the process, make your materials perfect. Okay, so advanced ceramics, these are the names. And also there's so in the traditional ceramics, for example, like you're very familiar with this, like the rice bowls and like what you need, and this is used in furnace. using constructions, okay, constructions and abrasives. Okay, these are the traditional ceramics. Okay, so the advanced. So in the advanced ceramics, there are also two types. Okay, so functional and structural. So how can we separate these two? What are the functional? What are the structural? Okay, very simple. Remember, structure, advanced ceramics, which means the materials used for the mechanical strengths. Mechanical strengths, which means your materials need to be strong, need to be hard, need to be tough, need to be ductile. So this one we call is a structural materials. So which means anything if the property, it is more related with the mechanical properties. Okay, for example, like automobile, obviously you need your car strong enough, right? Tribological, bioceramic, you put some biomaterials in the body, you have to make sure it's strong enough and tough enough, right? And the nucleus, okay, also need to, for the safety reason, you have to make sure it's very strong and tough, okay? So then what are the functional? Function is just very simple. Anything else, which means if non-mechanical, so anything else are non-mechanical, people use for piezoelectric, magnetic, optic, conductive, any other things can be used, we call it functional. So functional is a much bigger categories, okay, because why the separate this one? Because about, I think it's 1990, okay, many of you may have not even born right at that time. Before 1990, a lot of researchers, they very much focus on structural materials. Okay, so only about like 20 or 30 years ago, people start to do a lot of research on functional materials. Okay, because especially because of the handphone, all this microelectronics, as I said, right, 90% of the materials in the handphone, it is ceramics. Okay. So most of the, I think the one of the biggest drive for the functional ceramics is because it's semiconductors need the industry drive for this portion. Okay. Summaries. You have a take-home point page, right? So can you please summarize together? Okay. First of all, what are the ceramics? So ceramic is AB. At least AB, you can ABCD, at least AB. So A is metal or non-metal, B is non-metal, which means no matter what, you have to at least have one non-metal. Okay, very simple, at least one non-metal, then it's ceramic. What are the structures? So we said structures, we have different levels. So the subatomic level, for most ceramics, it is most ionic, but can be partially covalent. This is a very super important statement here. Okay, partially covalent. So why? Later we're going to explain. Okay, most ionic can be partially covalent. Okay, so atomic level, so we can have crystalline and amorphous, right? So among these crystalline, you have 7 crystal systems. Okay, so this is atomic level. Okay, the nano level, you have 0, 1, 2, 3, D. We said 0D, 1D, 2D, 3D. This terms used so often everywhere. Okay, so please make sure you understand it. 0 is a what? It's a dot. Okay, so 1 is a pencil, and 3 is a paper. Okay, 2 is a paper. So 3 is any other things if you have one dimension which falls into nano range. Okay. And the micro range, so which means you need to study the grain size, the shape and distribution, the grain boundaries, and pores and all the second phase, all these things. Okay, so the micron structures. Okay, so we also talk about what are the advanced and traditional materials. So the key difference is advanced materials, ceramics is orders of magnitude finer and uniform, no matter what, which means it is much better controlled. The morphology is much better controlled. Okay, and the structure and the functional. The structure, it is mechanical. Functional, which is non-mechanical. Okay, so I expect you know all this because as a material scientist, if you go to talk to people, so all these are very basic things. Okay, make sure you have these big pictures. We always start with big pictures first. Okay, so now Okay. So you can write down, or if you don't have time, maybe you can screen print. Screen print. Okay. Anyway, I'm going to give you a review before the quiz. So all these things I'm going to give you again. No worry. Okay. Screen print. Okay. So I move on now. Okay. So this one super important. This for this course this week. This is a VIP one. So now, how can we determine the crystal structures of ceramics? Okay, crystal structures. Crystal structures is which level? Subatomic, atomic, nano, micron. Which one? Can you type? Subatomic, atomic, or nano, or micron? Can you type, please? Yeah, excellent. Thanks, all of you. Yeah, atomic. Now we move to this atomic level. How can we determine ceramic, the crystal structures of ceramics? Okay, good. So continue. So there are three factors. Okay, the first factor, the crystal stoichiometry. The second one is radius ratio. The third one is propensity for covalency and the tetrahedral coordination. Okay, so even difficult to read, right? But it's super important later. Okay, so the first one is very straightforward. I think everyone knows, right? So the key word is what? Charge balance, right? This is a universal rule. You have to have a charge balance. Like a alumina, you have 2 alumina, 3 plus cation ions have to balance with 3 oxygen 2 minus ions. Okay. So the stoichiometry, so specific ratio of cation to ions, which maintain a net balance. Still the charge balance, you have to have the charge balance. So this is a very universal, you learn in your secondary school. Okay, so the number, okay, so the second, the terms, remember this one. This is a new terms, I think. The numbers of ions surrounding the cation ions is called the coordination number. The number of ions surrounding the cation ion is called the coordination number. So let's continue. So the second one is a radius ratio. The radius ratio. Okay. So first of all, so the ions normally is bigger. Okay. So how the ceramic arrange itself? So they always arrange the big thing first. So which means the ions have to be close packed first. Okay. So have to be large. It's always a larger one. The ions are usually larger. So most of the time that can be close packed. Okay, so the cation ions on the other hand are usually smaller, so they're going to occupy this interstitials, which means the space in between the crystal lattice, between and among the ions. Okay, so how can you remember this? It's just like you can imagine, ions is what? Ions is always accepting the electrons from cations, right? They're receiving something, so they're bigger. The cation is giving something, so they're smaller. Okay, so ions is larger, so close packed. So the cation ions stay in the interstice. Okay, so between the ions. Okay, so there's a very important principle here. The principle here. Okay, so this is a principle. The principle is the stable ceramics. Please really highlight this one. Okay, the stable ceramics. The ions surrounding the cation ions are all in contact with that cation ions. Okay, the key word here is in contact, which means no matter what, your ions have to touch the cation ions. Okay, so now I'm asking you, is this one stable? No, they're not in contact. Okay, but then this one is stable, right? Because it's in contact. This one is also stable. It's in contact. So you may ask me why. Okay, actually this is very much thermodynamic things. Okay, so it's low energy, stable. Okay, so stable ceramics. So the fundamental here is you have to make sure the ions surrounding the cation ion are in contact with the cation ions. Okay, so this is super important. Okay, so let's continue. So for a specific coordination number, so first of all, what are the coordination number of this one? B and C, what's coordination number here? If you don't remember what is coordination number, please go back to the previous page. What is coordination number? Can you write down in the chat box? So what is the coordination number here in the B and C? Okay, let me see. Excellent. Thank you, Janice, Jahua, and sorry, Mr. Ang. Okay, yeah, 4. Okay, so the minimal chi-ion ratio. So why this one? So there's a super important concept here, which is there is a critical or minimal chi-ion and ion ratio for which this contact have to be maintained. So what does this mean? So which one is a minimum case? Is B or C? B or C? So for a specific coordination number, so like B and C, the coordination number is what? Both of them are 4, right? Both of them are 4. But which one give you the minimal chi-ion and ion ratio? B or C? Excellent. Thank you, Hong Yu. Thank you, Lida. Thank you. Excellent. Yes. B is the minimum case. B is a minimum case. Okay. So there's a critical and the minimal chi-ion and radius ratio, right? So obviously this one can be bigger, right? So you can just draw. So the ions, you can draw a bigger sphere here. Am I correct? So this one is a minimum case, which means your ion have to, number 1, have been in contact with the chi-ions. Am I correct? Because this is a universal rule. You have to make sure your ions is in contact with the chi-ions. But if you want a minimum case, which means your ions have to also be in contact with each other. Okay, so that's the minimum case. The minimum case is what you can calculate, because once everything have to be in contact, so you can calculate the radius ratio RC over RA. Okay, so this is the, let's move on. Okay, so this is a table, super important table. Okay, so you can see when the RC over RA, if it's less than 0.155, so the coordination number is 2. If this RC over RA is less than 0.155, so it's 2, which means you're going to have 2 bound with each other. So if RC over RA is in this region, okay, so then it's going to be 3. Okay, so the coordination number 4. So if it's RC over RA, which is 0.414 to 0.225, so then it's going to be something like this, which we call a tetragonal. This is tetragonal. Okay, and if RC over RA, if it's in this region, so it's octahedral, so which is the number is 6. Okay, so you can see it looks very simple, right? Which means how your atom is arranged, it is actually related with your RC over RA. Then how can we prove RC over RA gave you this coordination number? Okay, so I give you one example. So after I explain this one, so we can have rest here. Okay, so demonstrate the minimum chi-ion and ion radius ratio for coordination number 6 if it's 0.414 for stable ceramic crystal structures. Okay, so first of all, I have already asked you, how can we calculate the minimum chi-ion to ion radius ratio? So first of all, we know, right, everything have to be in contact with the ions, need always be in contact with chi-ions. Am I correct, right? But if it's a minimum case, which means what? Minimum case, which means your ions also need to be in contact with ions. Okay, so that's the minimum case. So if we go back here, then you remember what I'm talking, which is a B case, right? You already answered my question. So B case give you the minimum. Once everything, everywhere have to be in contact with each other, so then we can figure out its geometries. Okay, so let's calculate this one. So first of all, you see these structures. Tell me, what's the coordination number here? What's the coordination number here? Excellent. Excellent. Okay. 1, 2, 3, 4, 5, and 6, right? So this guy is contact with 6. Okay. So this coordination number, which is 6. Now let's calculate the minimum case, which means you have to be in contact everywhere. So what they do here, they just use this plane, the top plane. So they can just calculate because you can see, so the ions here, ion have to be in contact with the kite ions. And also the ions and ions have to be in contact with each other also. Okay, so once you know this, then it's very easy for you to calculate, right? So you can see, then we simply just take out this triangle GHF. GHF. So this one is obvious, it is a right angle, right? So what is GH? What is GH? So if let's say this is R, radius of ions, which is this portion. Okay, then this will be the RC, right? RC. And for GF, actually crossing two ions. So it will be 2RA. So the rest is just very simple. It's just a right angle. It's just a triangle thing. Okay. So quickly, you can just quickly calculate this. One of the phases of the crystal structures in which ions are kind of just touch along the edges and also face this diagonals. So let's continue, right? So it should be very straightforward already, right? So GF equals to RA, right? FH, this FH is equals to GH, right? So it's equals to RC plus RA, right? So then just this two side equals to the other side. Okay, I think it's too simple for you. So put everything in, okay? RA plus RC square equals to 2RA, okay, square. So we can solve out this one very easily. So the RC over RA is going to be 0.414. 0.414. Okay, simple, right? Yeah. Okay, actually, this is going to be your tutorial question. I leave it you to figure out. So when the coordination number in this case is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so coordination number is 8. So let's calculate its RC over RA is 0.732. Actually, the same thing as the previous one. Same thing. Okay. So you can see, since we said this case is 414, let's go back 414 that table. This table is super important now, all right? So we say the coordination number is 6. So the minimum value need to be what? Need to be 414. This is a minimum value. Correct? Okay. Okay. So we finished. We said we have 3 criteria to determine a crystal structures. The first one is what? First one, give me the keyword. How can we determine crystal structures? The first one is the charge balance. Let me see. Stoichiometry, very good. Very tangent. Okay, thank you. Correct. Stoichiometry or charge balance. The second one is RC over RA. But is it enough for these two to determine? No. There's a third criteria. The third criteria. Okay, so now let's move on to the third criteria, the propensity for covalencing and the tetragonal coordinations. Now you remember, right? So just now we explained in the subatomic level, ceramics. So ceramic is not pure ionic. It is not pure covalent. It is actually a mixture of ionic and covalent. Okay, when it is more covalent. Okay, what I put here, when it's more covalent, propensity for covalency, which means if in the ceramic bonding, if it's more covalence in bonding between, you're actually going to get some what we call a tetrahedral coordination. Tetrahedral coordination, which means the coordination number is equals to 4, because this tetrahedral means you're going to have 4 planes. 4 plane tetrahedral. Okay. So how can we understand this one? So we just read through first. I'm going to explain next hour. In many compounds, the tetrahedral coordination is observed despite the fact that the radius ratio would predict otherwise. This situation typically arises when the covalent character of the bond is enhanced, such as when, actually when you read this one, it's very simple, which means when in the coordination, in the periodic table, when you are more close to each other, you are more covalent. once it become more covalent, so you even from that table, the RC over RA give you the coordination number is 6, but in the end, what you get is 4. Don't worry. So this one, we just read through first. So next hour, we're going to explain in details. Okay. So yeah, so let's have a 10 minutes break and see you in 10:30. Okay. Just get some water. Let me pause the recording. Okay. Okay, so very quickly, we review what we learned last hour. So ceramic AB, anywhere you have to at least have one non-metal. We said we have subatomic, is a mixture of ionic and covalent. That's the normal case for ceramic. Atomic, you can either have amorphous or crystalline. Among the crystalline, so we have to determine its crystal structures and the CN numbers, all these things, okay? The nano, you have 0, 1, 2, 3. And the micron, you need that determine grain size, shape, boundaries, pores, blah, 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 okay? Advanced and traditional, one orders of magnitude finer and more uniform. And the structure and the functional. So structural is mechanical and the functional is non-mechanical, okay? And also we said these are the 3 factors affecting the crystal structures. Okay, so this one is very general. Everyone knows the crystal stoichiometry, okay, charge balance. So the tricky thing is this 2, the radius ratio and the propensity for covalency and tetrahedral coordination numbers. Okay, so we said the first one is straightforward, charge balance. So radius ratio, we said only these 2 cases is going to be the stable case. You have to make sure your ions in contact with your kite ions. Okay, but the minimum case, which happens at when for specific same number, so there's a critical or minimum kite ion RC over A for which this contact can be maintained, which means that even the ions need to be in contact. So this one is going to help you to determine the minimal RC over RA. Okay, so I said this table is very important. This table, so we said CN2 is this region. Okay, CN3 is this region. So we have already calculated the CN6, which is the minimum RC over RA is 0.414. So in the tutorial, you're going to calculate when the coordination number is 8 and the minimum RC over RA is 0.732. So I leave you to figure out. So it's pretty straightforward. Okay. So, and also we spent some time, it's a simple math here, to determine that when the C number, if it's 6, so it gives to you this RC over RA is actually 0.414, simply based on this geometry, this triangle geometry of the GHF. Okay, continue. Okay, so the tricky thing is this one. As I said, I'm going to explain. Okay, so later I'm going to give examples. So first of all, so you can see what they said. If the kite ions with high polarizing power and ions are readily polarized, which means if they have closer electron activity, magnetic, which means in the periodic table, they're close with each other. Okay, like if the ions is sulfide, selenide, and iodine, like this 1, 2, 3, like all these ones, and also if the kite ions is also copper, zinc, aluminum, so all this one most likely they are going to give you some special things, which means that table cannot be used anymore. Okay, so the conclusion, remember the conclusion first. If the bond between the ceramic, it is more covalent. Okay, so you cannot use that RC over RA to determine anymore. Okay, no worry. So let's continue. So I'm going to again explain this one again. Okay, so first example, sodium chloride. Sodium chloride is 2. It is so ionic. Am I correct? Right? It's so ionic. So that's what we put here. It is highly ionic because we go back. Sodium is where? Sodium is here. chloride is here, so far away, right? These two are so far away. So obviously it's a very ionic case. So then it's very comfortable to use that table to determine. So we know the radius ratio is 0.56. Can you go back to your table? Tell me what's supposed to be the coordination number here. Please go to the table to tell me what is supposed to be the coordination number if the radius ratio is 0.56, because all this can be checked from the reference book. Excellent, excellent. Thanks, Tanjung and Alida. Okay, so yes, from that table we know if the RC over RA is 0.56, so the coordination number is 6. Is it true? So let's see, 1, 2, 3, 4, 5, and 6. Correct, right? Correct. Okay. So that's what we had. It is highly ionic. So that's why. So more or less like each of them are FCC. So the sodium is also FCC. The chlorine is also FCC. So these two FCC, they're sort of like interpenetrating with each other. So that's what we put here. So the two interpenetrating FCC lattice of this sodium and chloride. So this is a perfect example to tell you your RC over RA is going to work if it is super ionic. Sodium, chloride, right? Who can be more ionic than them, right? It's very ionic, okay? So use that table we know, because radius ratio you can check from any textbook, okay, or reference book, okay? So this is the first one, Now you can see, so this is the one we say is a rock salt structure. If you see any structure like this, so it's a typical rock salt structures. Okay, so let's continue. Okay, it's here. We just said somewhere in between here. So let me continue. Cesium chloride. Cesium chloride. Cesium. Where's cesium? Where's chloride? Chloride. You already know, right? Cesium is where? Cesium is here. Again, is 1A. So it's still very ionic. Am I correct, right? Very ionic. So if we go back, so this radius ratio is 0.94. So coordination number is what? This one is very simple. Quickly, everyone write. Give me figure. Okay, good. 8. All right. The simple one, right? It's nearly to 1 already, right? So it's 94. So its coordination number is 8, right? Is 1, 2, 3, 4, 5, 6, 7, 8. 8. More is like a BCC, right? Body center, but it's not a BCC. This is not a BCC because these are the two different things. You have cesium in cesium and the chloride because they are different things. Okay, but you can use some tricks for you to remember. Okay, because we always use something we're more familiar to remember something, some new things. Okay, so this cesium chloride structures is a little bit like a BCC structures. Okay, so 8 chlorine ions surrounding essential cesium cation ions at the half position. Okay, so this one like cesium boride, titanium. So all these fuels have similar structures. So this is a second example. Again, this one you can use the table or not. Yes or no? So I keep saying if it is very ionic. So you can always use 可以 Okay, you can always use this table to determine the coordination number. Okay, correct. So let's continue. Okay. Some weird zinc blend. Okay, so from the actually, if you calculate the radius ratio, it is larger than 0.414. So if it's larger than 0.414, so can you go back to the table to see? Tell me the coordination number is supposed to be what? 0.414, larger than 0.4. So it is actually supposed to be, coordination number is supposed to be 6. Okay. So it's supposed to be 6. Why is it 6? 1, 2, 3, 4. It's not 6. It's not 6 anymore. Why? Why it's not 6 anymore? Okay. So in this case, like this one, we call it a zinc blend structure. You have zinc and the sulfide. You have zinc and sulfide. Okay, so we said if larger than this one, you're supposed to have 6, but it is not. It is 4. It is we call it a tetrahedral structures. You have 1, 2, 3, 4 tetrahedral instead of octahedral. 1, 2, 3, 4, 5, 6. Okay, so it's different. Why? Which means you cannot use this table to determine anymore. So how can we, zinc, where's zinc? Where's zinc? Zinc is here. Sulfur is where? Sulfur is here. They are too close to each other. The electronegativity is too close. So which means now this one you have more covalent or more ionic, tell me. You just type C, tell me. Okay, anyway, yeah, it's more covalent. Okay, since it's more covalent, so we can go back to the criteria number 3. Number 3 are propensity for covalency and the tetrahedral coordination numbers. Okay, so we said in many compounds, the tetrahedral coordination number is observed despite the fact that the Bethe ratio would predict otherwise. Like in zinc sulfide, right? Just now we explained the case. The RC over RA is larger than 0.414. So from that table, we know actually the coordination number is supposed to be 6. 6, which means your coordination is supposed to be something like a 6, but it's not. It is 4. 1, 2, 3, 4. So it's a tetrahedral coordination number. So this is an odd case. Odd case, okay. So the odd case, which means if you have more covalent bond in between your ceramics, so you cannot simply only use this RC over RA to determine anymore. Okay, so this is a very special case. So that's what we put here. So if high iron with higher polymerizing power like copper, zinc, we just said zinc sulfide, right? Copper, aluminum, zinc, and iodide, selenite, like all this, the ions are very polarizable. So which means they have closer electron activities. So sometime, most likely, you're going to give a tetrahedral, which means your coordination number is equals to 4. Equals to 4. Okay, so this is a special case, okay. So okay, so actually we can nearly summarize for this binary case already. So binary case, we said we have 3 criteria. So the charge balance have to be universal for anything. So anytime you have to make sure you have a charge balance. Okay, so aluminum 2, oxygen 3. Okay, so make sure the charge is balanced. Okay, the second one, if the bond in between the A and B, if it's quite, or it is very ionic, so you can always use this RC over RA to determine. Okay, so use that table very comfortably. You can determine the RC over RA is going to equals to either 4 or 6 or 8. Okay, it's very straightforward. But the tricky thing here is the number 3 here. Number 3, which means once your A and B have a little bit more covalent bond, then you cannot use that table to determine anymore. So most likely, once you have more covalent bond, you prefer to bond in this coordination number, which is 4, which is tetrahedral case. Okay? Okay, So we now move to a little bit special one here, which is the ABO3. Now it's not binary. Binary, which means you have only AB. Now we have more than AB, right? ABC, ABC. In this case, it's ABO3. ABO3. It is a very famous one. We call it the perovskite structures. Perovskite structures is calcium titanate. Calcium titanate. So now you can see the calcium is stay at the corner position. Okay, titanium is a small kite ions. It is actually inside the, we call it the body center. And also you have oxygen ions, which stay at the face here. Okay, so this one is a perovskite structures, we call it calcium titanate. So in this case, so the chemical formula is ABO3. It's one of the most typical the compound with three elements. Okay, so the lattice parameter, some random thing here is 3.8967, and the name is perovskite. Okay, so you have a smaller titanium which is the body center, and you have a bigger kite ion which stay at the corner, and you have oxygen stay at the face center. Okay. And also in this case, we have to know something because later we're going to use it quite often when we calculate the percentage of atom in one unit. Okay, so how can we say the numbers of atoms of a given unit? Okay, it depends on how it was being shared with your neighbors. with your neighbors. Okay, so for example, if the atoms, the position of the atom is at the corner, okay, now in this case, right, there's a corner, this one is at the corner, right? So now you tell me how many neighbors, how many this cubic, so how many of this cube, you're going to connect it with these atoms, tell me. If at the corner. Excellent, thanks, Sean, thank you. Yeah, it's 8, right? You have upper 4, this side, back side. Okay, so you're going to have 8. Okay, that's what we're seeing here. So you can see if it's corner, you have 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we can see these atoms belongs to this unit. This unit actually is only 1 out of 8. Okay, so if you are at corner, so it is shared by 8 units, So you only can count as 1 out of 8, which means this atoms does not belong to this unit fully. You only 1 out of 8 of these atoms belongs to this unit. Okay. 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 If you stay at edge, so let's say if you stay at edge, once anything, if you stay at edge, so you're going to share with 1, 2, 3, 4. You're going to share with 4. Edge means what? Edge means here. If you something have here, this is edge. Edge. Once you have something there, the edge, you're going to share with 4. So that one we said you're going to share with 4 units. So now you can only count as 1 out of 4. 1 out of 4, 1/4. This only 1/4 belongs to 1 unit. If it's face, which means you're going to share with another one. So it's going to be shared with 2 units. So in this case, it's 1 out of 2. So why this one is important? Because we need to use to calculate how many atoms inside 1 unit. Every time we calculate anything, we always use 1 unit to calculate, okay, to avoid any confusion. Okay, so in 1 unit, so how many atoms? So for example, in this case, so calcium titanate, this one is perovskite, right? So we said before, so this one is what? What is the atoms here? This is oxygen, right? Oxygen, if you go back, oxygen up, okay? So the oxygen, so since oxygen stay at the face, so we said before the face where atoms actually shared with 1/2. Okay, 1/2. Body is easy, right? Body because it's in the body center. So body is always 1. Body is always 1. Okay, if it's edge, so it's 1 out of 4. And if it's corner, so actually you only have 1 out of 8. Okay, so this one is just simple geometry here. Okay, so now, so how can we determine in 1 unit? In 1 unit, so what is the number of all the atoms? So you can use if you have 1 atoms of body, so just simply 1 times the number of the body. But if it's face, so you have to times 1/2, because any atom, if we stay at the face, have to be shared with another neighbor. If we stay at the edge, you have to share with 3 other neighbors, which means you only have 1 out of 4. If you stay at the corner, so which is 1 out of 8. Okay, so that's the principle behind here. So you can see, now let's calculate. So tell me, in this unit, so first of all, how many titanium? How many of this B here? This easiest one, right? Easiest. Yes, thank you. Yeah, belongs to this unit fully. Okay, so it's 1. So how about oxygen? So oxygen, first of all, how many oxygen? 1, 2, 3, 4, 5, 6. 6, right? But you have 6. It's 6. But the problem is 6 atoms, oxygen atoms, does not fully belongs to you. So each of them can only have. We said face before. Face is Face is 1/2. So which means 6 times half. So oxygen is going to have 3. Okay. So calcium is at the corner. First of all, how many calcium? 1, 2, 3, 4, 5, 6, 7, 8. You have 8 calcium. Okay. So, but in this unit, actually, you only have 8 times 1 of 8. Am I correct, right? Because as we said before, corner, if any atom is there at the corner, you have to share with, altogether you're going to have 8 neighbors to share with you, share this little guy. Okay, so which means you have to be 8 times 1 out of 8. Okay, so yeah, that's why we get in the end, A is going to be 1, B are going to get 1, but oxygen is what? Oxygen is type, please someone type. Sean, Yungjin, yes, excellent. 3 because we said 3, because this one you have 6 oxygen, but you times half, so it's 6. That's why the chemical formula of this perovskite is AbO3, right? Calcium, titanium, oxygen, 3. Okay, so calcium A, 8 times 1 of 8 equals to 1. Titanium B, 1, 1, and oxygen, because it's a phase 1 out of 8. Corner, it is 1 out of 8. Okay, A, B, O, 3. Okay, so that is the same. How can we? Because we are going to use this concept later in the week 3. Okay, so make sure. Okay, this is only the first one. The other thing you have to make sure there's a charge balance. So you just go back to figure out by yourself. It is charge balance. Okay, so summary for this part, the crystal structure, it is the atomic level. We just said atomic level, atomic crystal structures. How can we determine the crystal structures? You need to have charge balance, You need to have RC over RA. So how can we determine RC over RA? RC over RA, please write down the keywords here, which is a minimum case, okay, RC over RA. So only you can calculate a minimum case. In minimum case, which means what? Which means your pi ion, okay, need to be in contact with ions. Okay, that's for sure for everything. But in the minimum case, ions also need to be in contact with ions. Okay, so that's the minimum one. You can calculate RC over RA. Okay, minimum. And use this RC over RA, we can calculate how many coordination numbers, okay? But please bear in mind, so that table, according to RC over RA, related with the coordination number, it is only applies to what case? Tell me. That table only applies to very, can you write down? Let me see. Very ionic case. Thank you, Yongjin, and thank you, Hong Yong. Okay, very good. So this case only applies to very ionic case. So once it's very ionic, so you can use that table to determine. Okay, so if you have a little bit more covalent bond, so be careful, So that table may not be applied anymore. So it's case by case study. Okay. And also we have learned rock salt structures. So rock salt very ionic, right? And also we know the RC over RA is 0.5 something. So if you check the tables, coordination number is going to be 6. So it's a rock salt structure, which will be coordination number 6, very ionic, and it's 2 FCC interpenetrating with each other. And also we have learned the cesium chloride, right? Cesium chloride, again, very ionic. So, and also the RC over RA is so high. I think it's 0.94, right? 0.94. So it's even close to 1 already. So its coordination number is 8 according to that table. So it is not the BCC. It looks like a BCC, but it's not a BCC. Use BCC to remember. Okay. Zinc blend, special one because it is more covalent. So from the RC over RA, actually supposed to be 6. The coordination number is supposed to be 6, but it's not. It is 4. It's 4. Okay. And also perovskite. Perovskite is AbO3 already. Just now we talk about binary. Okay, so if perovskite, AbO3, so the unique thing here is if it's corner, it is supposed to be 1 of 8. If it's at the position is at the edge, so it's supposed to be 1 of 4. If stay at the face, it's 1 out of 2. If its body is 1, it's simple. Okay, so that's the tricky thing of the perovskite. Okay, that's for the second part, the crystal structures, which is atomic level for the ceramics. So there's a very important concept here. very important concept here is these two are this one, the R silver RA, and also the ionic bond. These are the important concepts. I think these are the new things you never learned before. Okay. So the easy part now, relax now. Okay, the characteristic of ceramic and the applications. So we said, okay, ceramics are inorganic and non-metallic. So we said AB, if it's AB case, at least no matter what, it doesn't matter if AbO3 or ABCD, no matter what, you always need to have a non-metallic elements there. So it is going to be inorganic, so it's non-metallic. So obviously organic is polymer, metal is metallic. Okay, so it's a very unique one. Ceramic is bounded by either by both actually covalent and ionic, so they have certain percentage there. And in most cases, ceramic has better electrical and heat insulation property than metal. In most cases, more insulating than metal. Okay, and also ceramic is brittle and less ductility and has very low toughness. I'm going to spend 2 weeks to explain about this toughness because this is a fatal issue for ceramic. I'm going to explain why from mass and from fundamentals. Okay, so ceramic is brittle and less ductility and toughness than metal. And also the good thing is why your handphone have 90% handphone materials are ceramics. Okay, it's because it is very high chemical stability, high melting temperature, and of course, if using semiconductor, have very unique these electrical properties, but we didn't put it here. Okay, so these are some general things. So I think the most people are very familiar with. Okay, someone is talking? No, okay. So, but I give you some special things. Okay, anything if it's special, then you can win Nobel Prize. Okay, I'm just joking. Okay, we said ceramic is what? It's very electrical insulation, which means it's not a conductor at all, right? It's not a conductor at all. It's an electrical insulator. But some ceramic can be even like this one is ceramic, right? Is it ceramic? Is it ceramic? Which one tell you it's a ceramic? LSCO. LSCO is a very, very famous material. Okay, lanthanum, barium, copper oxide. Which one tell you it's a ceramic? Which elements? Yes, oxygen are as I said before, anytime if you have element, if it's non-metal, so we said it's a ceramic. Lanthanum is ceramic, strontium is ceramic, barium is ceramic, copper is ceramic. Metal, sorry, mistake. Okay, so all that rest is metal, but they have an oxygen there, oxygen, so it's a ceramic. So this ceramic is very special. So when the temperature is lower than 35 K, so it's going to become a superconductor. Superconductor, which means there's no resistance at all. Okay, so this is a Nobel Prize in Physics in 1987. Okay, for their important breakthrough in the discovery of superconductivity in ceramics. Special, right? Special, as I said, if anything special, very unique, you're going to win a Nobel Prize. Okay, and also this is another special one. We said ceramic is like your bowl, and most ceramic very tough and also very hard and very low toughness. Okay, but this is something special here. Which one is MAX? So M is early transition metal. So early transition metal is here. These are the early transition metals. Okay. Okay, early transition metals, and A is A group elements. Okay, and X is sometimes it's carbon, sometimes it's nitride. Okay, so like for example, like titanium silicon carbide, Okay, so this one, some special ones are this one. Okay, so this material is okay. So the advantage over the respective Stochastic binary transition metal carbide or nitride, which means combine. If you compare with titanium carbide or silicon carbide, so this titanium silicon carbide. Okay, so this one they're going to have better electrical and thermal conductivity. Interesting, right? Interesting. It's still ceramic, but they have good thermal and electric conductivity. They're actually not susceptible to thermal shock. And also it's easily to, like a machine, can just cut. Wow, interesting, right? Interesting. Ceramic can be cut, okay? Has specific stiffness, and it still enjoy the goodness of ceramic, which is still very chemical stable. Something interesting, right? They combine the good thing with metal and the ceramic. Okay, I just give you special things here, okay? And also, ceramic can be widely used in the, like we said before, like used in the thermal insulation, like this one, like aluminum nitride. Aluminum nitride is a very famous heat sink materials, like very much used in your handphone. Again, your handphone, your computer is a heat sink for electronic packages. Okay, like insulator, like oxide fibers such as silicon, alumina. Okay, so for example, I give you one example here. You can see this is silica fiber. Silicon fiber. See, one fiber. So this one's using the space. This uses space. Why it uses space? Because they have very high insulation. So why have very high insulation of heat? Because there's a lot of air in between. Okay, air is very good thermal insulator. Okay, so in this case, they just fabricate some like silica fibers. Silica fibers is used to support the strength of the materials. You cannot just use air, right? You still need something. You still need a piece of materials. So inside this piece of materials, you have silicon fibers, and in between the silicon fibers, you have large space which has air inside, right? So this air actually itself is a very good insulator. So they simply use silica fiber together with the air. The air is used as an insulator to provide very good thermal insulation properties. And it's very much used in the space, in the outer space, like astronauts things, okay? So space shuttle, that's what we hear, the space shuttle type, thermal barriers, high temperature windows, okay, because they have stand. You have to insulate the heat. And number two, you still need a little bit strength, right? You cannot just use something, just use air. How can you use air, right? Because air have no strength at all. You still need something with strength, but still have a very good thermal barrier properties, okay? You can say space, aeroplane, and engines are very widely used, okay? And also you can see there's a lot of examples here like electrical and the dielectric. I think this is one of the major things to drive ceramic to be very much used in microelectronics, like low voltage insulator, like insulation and semiconductor. So this one, semiconductors, non-linear IV characteristics, gas sensitivity, conductivities, and conductivities, ferroelectricities, okay? So there's a lot of different applications here, okay? And also can be used in magnetic and superconductors. So we just explained about this superconductor. So there's another even more famous one. That's what we call YBCO. This is also a very famous one. Why is so? Because if you put these materials in the liquid nitrogen, it's going to become a superconductor. Superconductor, which means they don't have any resistance anymore. Okay, so widely used in the high-speed train. It's very, very used, and also used in discrete magnetic, this machine, all these machines. Okay, superconductors and soft magnets and magnetic tapes, like a transformer cores, hard magnets. Okay, so you can see we put almost everything here: electro, ceramics, ceramic materials. Okay, and piezo electric ceramics, magnetic fluoride ceramics. Okay, so all these are very widely used. So I'll put some YouTube here. So if you want to watch a little bit more, so you can always watch it. Okay, and also optical. You have non-linearity, like a switching device for optical computing, and transparency, for example, like this Archipure silica. I think I demonstrated this before in 8301, right? How many of you went to 8301 before? It's another course I used to teach for year one students, material and man. Actually, I explained this material before. Okay, so you can see this is silica. It's actually inside is a silica, but used as optical fiber. So optical fiber actually even changed the word. So that's what you use in the internet. Okay, so it's also another Nobel Prize in 2009. So it's a silica fiber. So this is pure silica fiber used as optical communications, like in windows, translucent and chemical inert. Okay, IR transparency is used as optical windows. And also I bring this one in the class before for H301 material and man course. It's I think, okay, so you can see the silica fiber is something like this, which is even softer than your hair. So you can imagine it is a ceramic. But if you process in the micro range, it becomes like a hair, very soft. You can twist, twist, twist. Okay. So this is another one. And also like can be used as a dense one, a porous one, and transparent one. So this is transparent ceramics. Okay. And so this is NTU one, the YAG is used in laser, very famous laser materials. Okay. And fusion are these nuclear ones. I think I give you one. I said in National Day Rally in 2019, 100 billion need to protect Singapore against the rising sea level. So the series said nuclear power. The Singapore might consider nuclear power as one of the choice for the renewable energy. Okay, so it is much safer now. So that Singapore government even consider the nuclear power to be one of the choice for the power generation. Okay, and also like chemical biocompatibility. You have these anti-corrosion properties. So you have like this using as a teeth and bones, like in your body, bone implant. Is also a lot of market here, very expensive ones. Also, these are ceramics. Okay, so that's all, but make you happier. So this portion is not examinable. I just put it here to let you know how important and how ceramic is a huge important thing. They're very much used everywhere, but yet just let you know it is so widely used everywhere. Like as I said, the computer, your handphone, 90% of material inside your handphone is ceramics. Okay, so that is pretty much all for today. And as I always said, first week is always a simple one. The technical things, important technical things is this portion. It is part two. Part two is very important. So crystal structures. This portion is the VIP part of this week. Okay, so determine the RC over RA. How can we determine the crystal structures? And what are the crystal structures such as rock salt, cesium chloride, zinc blend? Okay, so all the things. Perovskite. So corner, if you stay at the corner, edge, face, body. So this week, week 2 or the section 2 is important. Okay. Okay, that's all. Thank you. See you after recess. So take care of yourself. Yeah, it's yeah, there's a lot of cases now. So please exercise more, eat well, rest well. Okay, still protect yourself. Stay safe and stay well. Thank you. Thank you.